I can tell I'm dragging on. I'm sorry. I know these 3-hour classes are tough, and I make it even harder. I try to break up like statistics with something, try to be funny a little bit once in a while, but sometimes that just gets terrible too. So I'm sorry if I've lost you. Let's come back. This next section I'll go through a little bit quickly, just because I'm just trying to prove a point that I said before. Each of those 4 methods to estimate a factor to identify the model give you identical fit, and the standardized estimates will be the same for all of them. So this is why we always, fit is, it seems really weird. I remember when I learned factor analysis, it was like, I have to set a factor mean and I have to set a factor variance. And I remember actually in grad school, all I learned was the standardized factor version of this, where I had a factor variance of 1 and a factor mean of 0. And when I started working here over in the psych department, everybody was doing the marker item. And I was like, whoa, that's different. And really, it's not that different. It's just a matter of, we pretty much only work in standardized coefficients for this reason. So when we report factor loadings, we always report the standardized versions, because they're the same regardless of which one of these 4 methods we choose. So it's a little bit more of a nuance than anything else. More often than not, the bottom 2, in SEM, we do the marker item because sometimes we want to go predict factors, and so that variance being estimated can shrink. It can be residual variance then. In IRT or in scale building, we sometimes don't do that. We just want a constant variance, maybe to equate with different years of the form or something along those lines. But it's 6 of one, half dozen of the other. And this is what this section of the slide try to show you. I give you in this section, and I won't go over the specifics of it. Let me back up. Throughout this class from now on, with the exception of one slide, we will do standardized factor means. Sorry, not standardized. We'll do marker items. Estimate the factor variance, set the factor mean to 0. There will be one slide in the invariance section where we switch over to the standardized, and that's because we want to test whether or not a factor loading differs by groups. And if we've set it to 1, we are making the assumption it doesn't. It's identical within groups. So there'll be one slide where that happens. But for everything that we're going to learn, it's going to be this bottom box right here where we estimate, set one item's factor loading to 1 and set the factor mean to 0. I don't know why I'm drawn to the screen when it's right in front of me. Gosh, thank you for putting up with my incompetence sometimes. But here's all the other identification methods. This is what we had just seen. This is the first. What I'm going to show you here, these are the, take a look at the standard. These standardized estimates right here, and then take a look at the log likelihood for our model. So this is all 4 identification methods, their output, and their estimates. So here, actually, this is not what I just showed you. This is where the factor variance is set to 1 and the factor mean is set to 0. And take a look at this. Isn't this interesting? The factor loadings are all equal to this standardized with the latent variable version. If I switch this up, let me see here. The syntax for this, how to actually do this, is to put a 1 right here by gambling to set the gambling's variance to 1. And then in the Lavon SEM function, there's a switch that you have to turn to true that talks about marker items, I believe. It's in my syntax if you want to see it. This is the same thing I just showed you. If I want to estimate the factor mean and estimate the factor variance, I have to set one of the items indicators or intercepts to 0. One of the indicator is an item. Sometimes we say indicator for variables we've observed in this analysis. You may see that. So we set that to 0. And we leave this code here. If we turn on, we go look at our output, you'll see here we get a 0 for that value. We get some type of variance intercept. But the main thing is look at our model log likelihood. It's the same. Negative 9564.556 is the same as we saw it there and the slides before. So big picture. Jennifer, you're looking terrified. Don't be terrified of this.
Well, it doesn't look like you did what you said you were going to do to me.
Uh-oh.
You're flipping through them, so I don't know which direction it is.
Yeah, let me back up. This is me. This is the wrong picture. I thought I had done my previous analysis, but this is a standardized factor. So I have a typo here. I'm sorry.
That's cool.
That shouldn't be, but if I flip back a few slides to my previous analysis, I still have this is where I estimated the factor variance and set the factor mean to 0.
Right.
I don't show the log likelihood here.
I'm cool with all this. It's like later you're setting all of the intercepts to values.
Yeah, I'm doing. Yeah, it's basically setting some to 0, some to 1. It's all the nuances of the program.
Okay.
We don't need to worry about it.
Seems important.
Honestly, not that important. Believe it or not. So long as you know what's going on, not that important.
Don't know what's going on.
Well, pardon me. The bigger picture is whatever we're doing with all that crazy stuff fits the same. And the results we're going to interpret are the same.
So what is the default?
The default is this marker item, where the first item on a factor loading is set to 1, and we estimate the factor variance. And the factor mean is set to 0, so we estimate all of the item intercepts.
So like a couple slides from now, I'm pretty sure it says in your syntax that it defaults to setting the factor variance to 1.
Does it say that? My
It's
goodness.
Green, there's green stuff
Where did I say this?
there.
Oh yeah. I'm sorry. I'll clean these slides up and put a new version of them online. My apologies.
It's cool.
Thank you.
Just trying to get a handle on it all.
Yep. Here, let me do this. I have a way to fix this. How about I grab the R code itself and just show you it. The R code should be right. I just copied and pasted the wrong pictures with it. There's no R code. It's over here. There we go. You can't see that very well, can you? View, zoom in. Okay, this may not be able to be seen very well, but the model 01 is the default, and all you really need to run it is this first set of syntax right here, which is just gambling equal tilde, and then the things that measure gambling. So all 5 items. The rest of this syntax is just showing you each of the parts that you can modify.
You're just writing out what happens by default.
That's right. By default, all that shows up. And the reason I do that is because now in each of these other models that I'm doing that are identical and fit, some of those numbers will change to go and produce the factor mean or the factor variance or otherwise.
But this is the real default.
This is the real default.
Promise.
If you just put this line of syntax in, the factor mean gets set to 0. We estimate the factor variance. And one of these items gets a marker. So the factor loading is set to 1 for it. That's it. All right? Cool. The next model I'm trying to run is the standardized factor. I did not show you the right syntax for it. Actually, I did show you the right syntax for it. What happens, the syntax is the same. This is the part where Levon starts getting all whack. But in the SEM call, like the function, you see this highlighted. I highlighted this to it. I added this std.lv equals true. And that says I want to take my latent variables and standardize them. So make their factor variance equal to 1, make their factor mean equal to 0 for all of them, bless you. So the syntax looks the same, but Levon's function changes all that, which is really not cool. In M+, you have to actually go and tweak things in the syntax. But when that happens, the output, the model estimates themselves, as you would imagine, the latent variables change. The factor loadings change because the scale of the factor now has changed. Instead of having a variance estimated to be 0.36, it's now a variance fixed at 1. So the numbers change. But take a look over on these right-hand columns. These standardized effects are the same as they were in the previous result. Standardized, always the same result. So it doesn't matter how we fight with Levon. Look at the standardized. Each one works. Right? Does that help?
Can I ask one question?
Please do. Please. This is great.
So in the book, it differentiates between completely standardized and standardized.
Yes.
Can you clear that up?
Absolutely. Completely standardized is what Levon would call the std.all right here. And what that's saying is not only do, here, let me try this. In a regression, in our path analysis, what we've seen before, a standardized beta, right? If we have y equals beta 0 plus beta 1 x, we look at beta 1, unstandardized, it's in units of y over units of x, right? So for every 1 unit of x, y goes up x number of units. std.lv standardizes by the factor but not by y. So that what that means is lambda for this goes up for every 1 standard deviation of the factor, y goes up however many units of the variable itself. So it's units of y per standard deviation of the factor, right? So basically y on my scale had, here you can see it. Here's each of the unique variances. They're untouched here because we didn't do anything to y itself. Fully standardized, and thank you for asking this question, is when this is std.all. That is when we're talking about standard deviations. For every 1 unit standard deviation increase in f, y goes up 1, or lambda standard deviation. Standard deviations of y per standard deviation of f itself. So that's why these numbers change here.
Which one do we want for having?
Either one gets reported. The main thing to do in your analysis when you're writing a paper or when you're looking at it is to specify which one you're reporting. But because they are, these two are the same regardless of, I guess either way, let me back up. My preference is the partially standardized, where the units of y still exist, because that helps describe the variable a little bit more. But that's me, and you'll see both reported. In fact, what happens in a lot of articles, you'll see them reported, and they won't tell you if it's partially standardized or fully standardized. But while we're on this topic, because I feel like I'm dropping the ball on explanation here, there is a combination that I do want you to see to help decipher them, right? Fully standardized, when you put this regression equation back together, fully standardized means that y should have, the overall y by itself should have a standard deviation. Oh my goodness, my writing is terrible. Y should have a standard deviation equal to 1. So what you should see is this number plus the loading squared should be equal to 1 in the fully standardized. All right. When you're measuring one factor and you fully standardize things, the loading squared plus the unique variance should be 1. So, always, regardless of what tweak you're doing to the syntax to get the model to run. Cool? Maybe? Yeah? So?
Close enough.
Okay. So, the other bits of syntax that you see, for instance here, this is where we have the, we are estimating the factor mean and the factor variance. So I put a 1 here in the marker specification statement just to sort of highlight that that first item is the marker item there. You don't have to have it there. It'll by default do that for you. And I put a 0 right here for the first item's intercept. That is the marker intercept to estimate the factor mean itself. When you estimate that, here is what you get. Same log likelihood, so it's the same model and the same values in each of the standardized boxes. By the way, the standardized values for intercepts are just crazy to me. I don't even know what they mean. The intercept doesn't go up however many units, so dividing it by some standard deviation doesn't do anything for me, right? So, finally, the last way that we do this, the last one, Oh, nope. Boy, I have messed up all these slides. I need to redo all these. Oh, here we go. When we have a factor variance equal to 1, but we're estimating the marker item intercept. That's where we turn back on this std.lv equals true in the SEM statement. It's crazy, but we get the same results. So I'm dwelling on the first thing, right? We have a marker item. We're going to estimate the factor variance. And then what we're going to report are the standardized factor loadings for everything. Okay? Ironically, since Jennifer, you brought this up, I'm going to keep picking. I don't know why I'm picking on you. Sorry. Thank you for being willing to ask questions. I like that. But because you were so gracious in asking questions, this std.lv, this partial standardization where we only standardize based on the factor, gives us the factor loadings that would have been had we had a standardized factor identification. Right? Because we've set the standard deviation to 1 for the factor. Right? Here. So this set of loadings right here, in this slide, we have the factor variance set to 1, which means the standard deviation of the factor 1. We've essentially estimated them as that. Right? So it's very arbitrary how we standardize the factor, and that's because it doesn't exist. So we're going to pick one and stay with it. And we'll drill that into your head, okay? Or I'll drill that in. Drill that in. I won't drill that. I'll keep talking about it. Hopefully it becomes more familiar. It sounds like the dentist. Have I told you my dentist story? Probably have. I went to a dentist in Athens, Georgia. She said, "Oh, what do you teach?" I said, "Statistics." She said, "Oh, we have things in common. Nobody wants to see you either." Exactly. So me talking about drilling makes me think of the dentist. Anyway. So moving on from that, we have one other thing we have to consider. In a path analysis where we have a latent variable, a factor, not only do we have to pick its mean and variance, or pick its identification, we also have to ensure we have a sufficient number of items to estimate. So a one-item model cannot be estimated because we have too many things that we don't know, right? Even if we set the mean of the factor to 0, set the variance of the factor to 1, right? We'd have a factor loading that we couldn't figure out what it is because we've already, the item, all it has is a mean and the variance to it, and those get described by the item intercept and the residual variance. So there's really no way we can do that with one item. So the short story for all this is if you're trying to build a scale and you're trying to test whether or not those items measure a factor, you need 3 items to be just identified. Do you remember that word from last week? That means the same number of model parameters as there are parameters in your saturated model, which means 3 items tells you your model will fit perfect. So you can't actually test the factor fits because the test will always return the same value. Yes, it fits. There's 3 items. That's it. 4 items, if you add 4 items to the analysis, you can actually test. You'll get 1 degree of freedom. There'll be more saturated model means, variances, and covariances than there are factor loadings, item intercepts, and unique variances. And you'll be able to test the hypothesis that this factor is measuring, being measured by these items. Right? So 4 is kind of the standard. Now you can, if you have more than one factor in an analysis, you can sometimes get by with 2 and 3 and be able to estimate and get parameters. But we're just talking about 1 today, so 3 and 4 is where we're at. And here's why. Here is a picture of a model. We have 2 observed variables. So these 2 observed variables are our data. So if we were to put this into these into a model, we would have in the saturated model how many parameters? How many means? 2 means, right? In the covariance matrix, how many variances? 2. How many covariances? 1. Right? So we have a total of 5 model parameters. So take a look at how many model parameters we'd have to estimate. Let's imagine we go and make it real easy here. Here's either either identification of the factor. If we use the marker variable technique, we need one item factor loading. We need one factor variance. We need, in this case, one factor mean, one item intercept, and just mining them. Bottom line is either way, any way that we pick to standardize this, marker item, standardized factor, or however, there are 6 parameters we need. But there are only 5 numbers we can get them from. So we have negative degrees of freedom. It won't work. So, let's move up a notch. Here we go. We have 3 items. In our saturated model, how many means do we have? 3. How many covariance? What's the size of our covariance matrix? 3 by 3. Excellent. So 3 variances, 3 covariances. That's 9 things. Right? This side's the standardized factor. We've set the factor variance. We've set the factor mean. So each item gets 3 loadings. Each item gets 3 intercepts. Each item gets 3 unique variances. That's 9. If we pick a different standardization, we still come up with 9. So always we have exactly, perfectly fitting, and the number of degrees of freedom for one and the number of degrees of freedom for the other are always equal. So we are identical to our saturated model. So model fits perfect. You will hear people running around, make them sound like they're scandalous. You will hear people in certain, with SEM backgrounds saying that, oh, having a factor with just 3 items is best case scenario because it fits perfectly. Oh. Have you ever heard that? Anybody ever heard that? I heard that here on this campus, and it was in the conversation of a 3-legged stool. 3 points define a plane. Ever heard that before? Ever seen a 3-legged stool? You can sit on a stool with 3 legs, but it's not very stable. 3 items will give you a factor. But those 3 items, if you really were looking at the factor and wanting to give somebody a score for it, or wanting to, no, there is no score, there'd be a lot of error in the estimation of that factor. There's only 3 items. Right? If you took a 3-item GRE test, would you be happy with that to go to grad school? Or better yet, the person who's going to operate on you had to pass a 3-item exam, right, to be certified as a surgeon. Would you feel comfortable with that? Probably not, right? Ironically, as a professor, I had to pass no items, but, this is why this lecture seems like it's going down in flames at the moment. So, 2 items can't do it. 3 items can do it. It's just identified. 4, and actually here, if this was our covariance matrix, right? Imagine this was our covariance matrix. We can see what each of the variances and covariance should be, right? If we have factor loadings A, B, and C, we can go and say that the product of those should give us each of the covariances between them. So we have 3 equations and 3 unknowns. We can do a little bit of algebra and get what each of the A values should be themselves. But an over-identified model is the best situation. This allows us to test whether or not the factor is present. Technically, we're testing it with 3. We just know the answer always. So with 4 variables, we have 4 means in our saturated model. We have 4 variances. We have 6 covariances. Is that right? 4, 4, and 6. So it's 14 total parameters. And regardless of how we standardize or how we estimate things, we actually have only 12 parameters we're estimating. And so that's it. This is the neat thing about the factor analysis. Remember last week or the week before I showed you that graph that had the number of parameters in the multivariate normal and it had the bendy line for the covariance? As you had more variables, the covariances and variances went up. I call it the curse of dimensionality. The factor model sort of removed that. Right? Because even though the saturated model is getting more and more and more terms because of those covariances, the factor analysis is going up linearly. But I will tell you, the more variables you put in, the harder it is for the factor analysis to fit all of the covariances. There's just more space it needs to absorb. Questions on this? So identification of factors happens in two ways, right? We have to pick the scale. We have to pick the mean and the variance. And what we're going to do from now on, with the exception of one slide, is set the factor mean to 0 and estimate the factor variance by setting one of the items loadings to 1, marker items. And then the other thing we have to ensure is that we have enough items to measure the factor itself. Now, on the education side of the world, like for tests that we have here, we have tons of items, right? How many items are in the CAP test? Anybody? Dan, you work at CAP. Do you know how many items are at the end of the year for one of the grades, one of the forms? Okay.
For 2010, about 70.
So 2010's form was 70 items, right? Now, we're not treating those as multivariate normal because they're all scored correct, incorrect, or they have a graded response with 0, 1, 2, or something like that. But if they were continuous and we could put these in multivariate normal, you could see how the model for it would be, you'd have a ton of parameters. You'd have a ton of degrees of freedom. But that's essentially what we're saying. Okay, so that brings up the dirty topic in CFA, model fit. Not really dirty. It's the same thing we learned before. If our hypothesized structure is a testable hypothesis, model fit is our test statistic. And all of the model fit statistics are the same as we saw last week, so long as we have multivariate normal assumptions. Right? Do you remember them? We've talked about them now, I guess, for 3. This is our 3rd week in a row talking about them. Root mean square error of approximation, RMSEA. That one we want to be low, less than 0.05. It's a root, right? CFI, TLI, those are indices. We want those to be up by 1. Same thing here. Standardized root mean square residual. That's the difference between your model's covariance matrix and the saturated ones in terms of standardized terms. On average, we want that to be small because it's a root. And then, of course, there was that hypothesis test, the likelihood ratio test between the model and the saturated model, your model and the saturated model, which we prefer. That's the strongest test, but that one never fits. So, same thing. Here we go. Here are the results. This is from any of those 4 models I just showed you to build up here in that really terrible section of class where I was trying to show you syntax that didn't quite work. These models all give the same fit because the log likelihoods are the same. So up top, this is our test statistic. This is the likelihood ratio test between what our model says the covariance matrix should be in the mean vector, what the saturated model is. And its p-value is 0.004. So based on it, we wouldn't say there's good fit, but that's normal. All right, so I'll put a negative here. This is boo, negative, minus. The next part that we look for model fit, I like to look at the RMSEA. That value is 0.043. That's where we want it to be. We want it to be usually less than 0.05. Yes. When I see that, the first time I run an analysis with someone, I'm just like, you've literally gone gambling and hit the jackpot. Now, that is hard to find off the bat, right? And in fact, these 5 items, I took 41 items, and I ended up with 5, purely because I was like, what are the best 5 I can find? The whole 41 don't fit well at all. The CFI and the TLI, we like those above 0.95, and look, they're right here. They are both in the spot we like them to be. The standardized root mean squared residual, sometimes people say less than 0.08, but that's also good. So even though the likelihood ratio test was a no, we have goodness of fit from all the other statistics. We would say this model fit pretty well. So there you have it. Just another note, the AIC, BIC, these things are for model comparisons that aren't nested, just to remember. And the model test of the baseline model is testing the saturated model versus the independent variables model, right, to see if there's any correlations whatsoever. And now you can see why the correlations matter so much, or covariances. Because if there's 0, then all the factor loadings will be 0. The model will fit perfectly, but you'd have no story. If all the factor loadings are 0, you're not really measuring anything. It's all error. So, because of that, we can interpret the parameters of this model. If this was an analysis you're running, you'd say, okay, I'm going to go estimate these parameters. I'm going to check model fit. Model fit worked. Hooray. Check the parameters. And here's how we typically interpret our parameters. The factor means, forget them. We don't talk about them. The factor variance, don't really talk about it either. Yeah, factors vary. That's all called individual differences. We're happy with that. Item intercepts. We don't really talk about those. But you know what we talk about? We talk about unique variances, although not directly. And we talk about factor loadings. So when we do a factor analysis, we want to know the factor loadings and the unique variances will combine to tell us how much information each item contains about the factor itself. So all the other stuff that you see doesn't get reported, and if you're reporting the standardized results, the standardized estimates, particularly std.lv, actually either of them, it does that, that means the factor mean and variance are set to 0 and 1 respectively. We wouldn't have anything to report on those for all of those every time you report standardized. So, the factor loading is just what we were saying a few slides ago. The increase in your predicted response of y for every 1 unit increase in f. That is the unstandardized version of that. So here are a comparison of the marker item and the standardized factor, right? This is marker item, right? Remember, this is where we set where the mean for the factor was set to 0 and the factor variance was estimated. And down here, the mean for the factor, the standardized factor, was set to 0 and the factor variance was set to 1. Right, so that's the difference between the two of those. If we look at the unstandardized estimate, we would interpret those just as we would in regression, right? For every 1 unit increase in f, each of the items' score goes up by lambda's points. So that first item, even though we fixed it, we can still interpret it as an unstandardized way of saying, as factor goes up 1 unit, the item response to this item goes up 1. And for us, that means literally, if somebody's gambling factor goes up by 1 unit, their score to item 1 goes up by 1 category. It goes from agree to strongly agree or something along those lines. That's how we would the raw unstandardized weights are on the scale of the variable itself. Now, like we talked about last week, I remember I had a couple of you sort of interpret some of the beta weights in the regression. What's 1 unit of the factor? 1 unit of the factor depends on its standard deviation. So f has a variance of 0.363. The square root of 0.363, what was that? 0.6? 0.6, thank you. This is the factor's standard deviation. That's the standard deviation right there. So what I'm saying is a 1 unit increase in f is about 1.5 standard deviations, right? It's not quite, but 1.5 standard deviations. If this is 0.6, it's about 0.9. So it's nearly 1.5 standard deviations more. So that's saying is factor goes up 1.5 standard deviations, right? So when you look at the standardized factor CFA results, they're estimates that are unstandardized, even though they're right out of the computer. Because of the way that we set the factor variance, the standard deviation for this factor is equal to 1. So a 1 unit increase in the factor is really 1 standard deviation. And that's why these numbers change, right? For 1 standard deviation versus 1.5 standard deviations, right? So that's all, the accounting all works. What's fuzzy is what the factor variance happens to be. So these unstandardized would say for every 1 unit increase in the factor, a person will go up 0.602 points on the item itself. Units of the item. And so finally, going back to what I just, when we were talking about different types of standardizations, because we've set the factor variance, that is a partial standardization. So that std.lv column, these estimates for factor loadings are identical. Right? They're just saying for every 1 unit or 1 standard deviation more of the factor. Well, that's exactly what our factor is. Standard deviation is 1. Right? So for every 1 more standard deviation, it's the same weird thing. So standardized factor loadings, I just mentioned that. The std.all, if you want to actually compute them, you could take the raw unstandardized loading and divide it by, or multiply it by the standard deviation of the factor, divide it by the standard deviation of y. You can come up with what those happen to be. The std, this is, I think that's what I'm using here. So, actually, I use std.all here just to show them. Either way, it's the same. 6 of one, half dozen of the other. Here, what we interpret std.all to be is for every 1 standard deviation more of the factor, the item response goes up, in this case, 0.594 standard deviations. The nice thing about the std.all column is it also represents the correlation between the item and the factor that you're measuring. So good items have high correlations with the factor itself. So here, the first item has a correlation of 0.594. That's what we're saying. And you'll note that's the same thing down on the bottom. Remember, the difference between the top and the bottom is just how we've gone and identified the factor itself. std.all is the same for both of those. That means for 1 standard deviation more of factor, y goes up 0.594 standard deviations. So it's taken into consideration. Oy. Questions? I can tell standardization might be the worst topic that I've described. It might be the way I presented it, but everybody's like, I feel like I've lost you, or just either lost you or boring the heck out of you. Maybe both. I'm sorry. The presentation for this has been not my best, and so I'll try to clean up the slides and talk about it a little bit more next week. What do you have questions on that I can try to answer right here while we're with you? Yeah, Bridget.
So we would just really have to know the marker.
Yes, that's it. That's it. If you just focus on it, you're fine. Focus on that to make the program work, and report from one of these 2 columns. That's it. If you do that, everything works out. As you go further into life, you can understand the rest of it. That's how I did it. I learned it the opposite. I learned it as factor mean of 0, factor variance of 1, and once I became a professor, I figured out the markers. So we just focus on the marker item for this, and we'll call it good. Okay? There's a picture. How pretty. Now, finally, one thing we can talk about for each item is that we can talk about how much variance is accounted for based on the factor. That sort of drives me crazy. Right? We have this thing that doesn't exist, but it's going to explain our variance for us. Doesn't that seem weird? No? Yeah? No? You don't think so? That's fine. If you think of variance accounted for as the difference in your residual variance between the model that's empty and the model where you're predicting the variable, then that's computable, right? We should be able to see this here in our analysis. And sure enough, this is the syntax to get your R squared. We can talk about how much variation is accounted for in each item by the factor itself. What we'd like to see, the better the test is, the more informative the test is about the factor, or better yet, the more reliable the test is, the higher these R squareds are. And if we have a factor that describes 100% of all the variance for all the items, that is equivalent to us saying we have perfect reliability. Our reliability is 1. So amount of variance explained, kind of you think about, well, what's left over from that? That's the unexplained stuff. That's that unique variance out there. So, other questions? Do you like it? I see the smile. That's a loaded question. Huh? Is that what you're thinking?
What a question.
What a question. This is, well, the thing is, that's cool if you don't. I mean, you join, like, everybody who's not in the social sciences, like all the statistics people, like, hate this stuff. Hate. I can't describe hate with a hate, like, just like passion, which is really odd. It's when you show them the statistics behind this version of it, they're kind of like, oh, I guess that's okay. It's assumptions. We're testing assumptions. That's what we're doing. Standardization, painful. Identification, the way I presented it's really bad. But let's just stay with the marker items. Maybe next year when I teach this, or I guess I teach it 2 years from now, I'll just teach you the marker item at first, and that'll be the nuance from it will hopefully leave that alone. Okay, maybe I'll leave that alone. And that's probably why when I learned it in grad school, my professors only did mean of 0, variance of 1 for the factor, so that we learn it all and then we can go and generalize later on. Does that sound like a good strategy next time for me teaching? All right, I'll remember this. I don't know. Yeah, that's the thing. It's a small sample, right? Thankfully, I mean, it's tough. I'm sorry. I apologize to you if I was unclear. Anyway, I dig this stuff. The reason why I dig it is I think the science behind it is cool. I can't get around Likert items being treated as continuous. I think that's the bigger flaw in what we're doing. But if I allow myself to, then what we're doing here is setting up a nice empirical way of testing whether or not what we're measuring is actually happening, right? Had I rejected this hypothesis, I would have not had a gambling scale. Right? I would not be measuring gambling, or maybe I'd have to throw out items. Maybe items weren't doing it. Next week, what we're going to do is build a scale with factor analysis. We're going to put it together. We're going to take those gambling items, and we're going to estimate one factor, and we're going to see how well it fits. We're going to find it doesn't fit well. And then we're going to start to weed out items that don't fit well, or we're going to start to modify it to make this work. But just like in path analysis, where we started the class, if the model doesn't fit, all of these estimates get bent out of shape. They get pulled in directions they shouldn't be. And what ends up happening is every other type of analysis that you do, be it with adding things together from the factor, or be it with in the structural equation model where it's all simultaneous in one analysis, all that gets biased. So we want model fit to happen first, and if we don't get model fit, then all of a sudden bias happens and our story gets told differently. So how is a factor analysis like a path analysis? I would say it is a series of regressions, simultaneous regressions. It's not like a path analysis in that the exogenous variable is not observed. Isn't that crazy? Yet we can still get estimates. We can get estimates because each of them correspond with some type of parameter in a saturated model. There's no F's in our model predictions. We don't even need to worry about it. We can just use optimization to figure that out. What model constraints must be made to identify a factor? Well, we need to figure out what its mean is and figure out what its variance is. And so for us from now on, we're going to say the factor mean is 0, and the factor variance is estimated because we've set one item's factor loading to 1. What data characteristics must be present to identify a factor? Oh, that's fun. We need 3 or more items for one factor. If we have 3, we have perfect fit to a model. If we have 4, we have the ability that may not be perfect fit. And what are standardized factor analysis coefficients? What are our factor loadings? Those are describing the increase in the outcome variable in standard deviations of it per standard deviation of the factor. That's the std.all. Or std.lv, which is standard deviations of the outcome variable, units of the outcome variable per standard deviation of the factor. Right? So partial standardization is the std.lv. Full standardization, std.all. Okay. Big picture. Our regression equations contain latent variables. It's important to realize those factors don't exist. right? They really don't exist. There is no score. It's crazy. Goes against everything you've learned ever since you were probably in kindergarten. All right? Do you remember the first test you ever took? That's a good question. Or survey? Anyway, they don't exist. What you have is survey items. If the survey items are good, then you have a good sense of what they're measuring, and what that goes into helps in a good study. If the survey items are bad, then you have nothing. You don't have a factor. Doesn't matter what you do to them. You have to go and do something. Drop items, pick out the ones that fit best, and go forward with that. So, in the big picture, we overlook this all the time in social sciences, right? We have a scale. That's the scale. Period. That's it. That's the scale. We don't even look. I used Stanford Binet. That's my IQ test. That's IQ. That's intelligence. That's not even a question. It's like a personal state of being is the score on this test. Right? I mean, you think about it. We become our score after a while, which is really ridiculous. And really, it's arbitrary. It's arbitrary as to what variables go in there, what forms of the test, how well it fits. What we're going to see next week is that a lot of times in building a scale, we're going to measure gambling, darn it, and we're just going to drop everything that doesn't fit our model. And our version of gambling might be different than if we had if Hong Ling had decided to study it with a different set of items and a different sample, and your construct of gambling and my construct of gambling might be slightly different. It's like Stanford Binet versus Wechsler versus whatever for intelligence. And so it's the items, right? It's the items themselves. So everything that we do will come back to the items. Their covariance matrix, particularly in our class, and we are going to be limited by the laws of statistics, right? We have sample size to worry about, and we have to worry about the variability of estimates and covariances. So if you only have a sample of 100 people and you're going to go and build a test that has 300 items in it, it's not going to work, right? You're not going to have the sample size to get all good stable estimates for everything. Anyway. Okay. We're going to go through this the rest of the semester. Factor analysis will show up every week from now on. Every week. So this is a first introduction. The next homework will have factor analysis. You'll be doing an analysis with it. That doesn't come out for another 2 weeks. So if you didn't get it all today, that's my fault. I apologize. I will try again and do better next week. All right? Thank you. Have a good week. Yeah, absolutely. Actually, hang on one second. Let me make sure we're off.